Hi, welcome to lecture 17. This is about derivatives of log functions. And as I said the other day in class, logarithms really are your friend, so you need to get used to dealing with them. And this particular topic, this particular lecture, should show you why they're so valuable, or give you an idea of why they're so valuable. So the first thing we have to do is start with the question of what is the derivative of the log of x. And we haven't answered that yet. So we'll do it in a slightly roundabout way very quickly. And we'll start with this equation that relates the log of x and its inverse, which is the exponential function. So if you write down that equation, which relates the exponential function e to a power and the log, which is natural log, of course, then the equation is e raised to the natural log of x equals x. Of course, you could do it the other way around, log of e to the x equals x, but this is the one that we're going to use today, and it is going to give us the derivative of the log. Well, first of all, this is the statement that the exponential function base e and the natural log function are inverses of each other. You do one and then the other, and they cancel each other off, so you're back to where you started from. Okay, with this equation, what I want to do is take the derivative of both sides. So take the derivative with respect to x of that, and that's got to be the derivative with respect to x of the right-hand side. All right, and we've done this kind of thing before. The right-hand side is pretty easy. The derivative with respect to x is 1, so I'm just going to write that right here on the far right. But what is the derivative of that mess? Well, the derivative of e to any power, as you know, is e to that power again. So I just write e to the natural log of x. Except that the chain rule has something to say and says, oh, wait a minute, that's not x up there. That's a function. And so therefore you got to multiply by the derivative of that function. So times the derivative of that thing that's up there in the exponent, which of course is the derivative of the log of x, which we don't know. However, and here's the cool thing, here is the derivative of the log in an equation. So I can just solve for it. The derivative with respect to x of the log of x equals 1 over e to the natural log of x, which looks kind of horrible until you remember that e to the natural log of x is just equal to x. And so we have 1 over x, which is not a bad formula. The derivative of natural log is 1 over x. So that allows us to take derivatives of all kinds of stuff. So for example, what is the derivative of the natural log of the cosine of the natural log of x? Nasty enough for you? Well, just don't panic. Just take it slowly and look at this mess inside from the executive's point of view. From the executive point of view, that's details. You don't want to worry about the details. What are you taking the derivative of? The answer is you're taking the derivative of the log of some horrible thing. And how do you do that? Well, we just did it. The derivative log of anything is 1 over that thing. So we just write 1 over whatever is inside here, which is cosine of log of x. And then, of course, the chain rule comes along and says, oh, you're going to multiply by the derivative of what's inside. Well, that's too complicated. I'll just write it. The derivative of what's inside, cosine of log of x. And see, the neat thing here is that you can take each of these things as a separate problem. So the derivative of the cosine of the log of x is just a separate problem. You can do that on a different sheet of paper if you like. I'm just going to keep going here. 1 over cosine log of x from before. But then I got to multiply by the derivative of this thing. Well, what are we dealing with? We're dealing with the cosine of some horrible mess. But that's no problem. The derivative of cosine of anything is minus the sine of whatever's there. Minus the sine of the log of x. Almost. Once again, the chain rule comes along and says, oh, wait a minute, there's something in here that's not x. So you're going to multiply by the derivative of what's inside. The derivative of, finally, log of x. And we just did that up at the top. So our final answer is going to be 1 over cosine of log of x from before. Then I get this minus sign. Let's put that minus over there. And then we'll get a sine of log of x. And then you get this derivative of log of x, which we now know is 1 over x. Now, I'll bet you $1 that if this were a textbook problem, which it is, but if it were an odd-numbered textbook problem, here is what you would see in the back of the book. They would have an answer like this: minus tangent of log of x divided by x. And you'd be scratching your head, maybe wondering where that tangent came from, but of course that's because sine of something divided by cosine of something is tangent of that something. All right, enough for that problem. No, you don't have to simplify it down to that. This is a perfectly good answer. That's not, I don't consider that to be any simpler. Okay, let's turn our attention to a different log. What about the derivative of the log base 10? Well, if you remember your experience with 10 to the x, the derivative of 10 to the x is just like the derivative of e to the x, except you end up with a fudge factor in there. And the same thing's going to happen here, not quite the same fudge factor. So what you say is, well, I don't know what the derivative of log base 10 is, so we let y equal log base 10 of x. And that doesn't help us, except it gives us a name for the unknown. Let's see if we can unwind this by taking this in its exponential form, which would be 10 to the y equals x. And then from there, we could take the log of both sides, take the natural log. Now, why would we do that? Why would we take the natural log of 10 to the y and say that? Of course, we can do it. We can take the log of both sides, because if these two things are equal, their logs are going to be equal. That's not the question. The question is, why would anybody in his right mind take the natural log of both sides? The answer to that question is that we know the derivative of this guy, natural log. We don't know the derivative of log base 10. And what we're doing is we're shifting bases from log 10 to natural log. So when we do this, this y is going to pop out as a multiplier. That's one of the rules of logarithms. So we get natural log of 10 here with the y on the outside equals natural log of x. And here's the thing. Y is now equal to 1 over natural log of 10. We're moving this guy to the other side, times natural log of x. And you see what we've done? Y was the thing we didn't know, that log base 10 of x. So the log base 10 of x is nothing more than the natural log of x multiplied by this fudge factor, 1 over natural log of 10. So that means the derivative of this is just going to be the same thing as the derivative of this. And this is nothing but a constant. It sits there and watches while you take the derivative of natural log. So the answer is 1 over natural log of 10 times 1 over x. So yeah, we have a formula for the derivative with respect to x of the log base anything, log base b, where b is a constant. And that's going to be 1 over natural log of b times 1 over x. And yeah, this formula comes up so many times that you probably are recommended to memorize it, just like most of you have memorized that the derivative of b to the x is b to the x back again, almost, times the constant natural log of b. So it's not too hard to remember. When it's the exponential function, the fudge factor is just the log of the base. When it's natural log, when it's the log base b, the derivative is going to be 1 over the log of the base times 1 over x. Okay, so let's turn our attention now to one of the more useful things that comes out of knowing about logarithms. And that is, oh wait, one last comment about this. Notice that going from here, where I said let y equal log base 10, all the way down to here, that is all of this stuff. The only thing I did from here to here was just algebra. So in a sense, and in fact even to the last step right here, this is all algebra. The log base 10 of something is 1 over the natural log of 10 times natural log of x. This is sometimes called in algebra a change of base formula for the logs. So you can change one log to another. And so this is just an algebra trick to allow you to take the derivative of log base anything. You write log base anything as 1 over natural log of that base times natural log of x. Okay, let's turn our attention to this very useful practical kind of thing. Well, practical in a sense. It's got a fancy name. Logarithmic differentiation. Used to be extremely popular. Now with computers it's not so popular anymore, except that you do still have to know how to do it, because it pops up every once in a while as a very handy little tool. A lot of times it used to be used to simplify computations. So here's an example where it simplifies a computation. It's not absolutely necessary, but it simplifies one. Suppose that your problem is to find y prime, where y equals this big horrible mess, x to the 3/4 power times the square root of x squared plus 1 divided by 3x plus 2 to the 5th. This is one of the examples that the book uses. Well, we know how to do this problem already. Not that anybody would like doing it. You take you look at it and you say, well, this is a quotient, so we have to whip out the quotient rule. Denominator times derivative of the numerator minus numerator times derivative of the denominator, all over the denominator squared. Well, when you go to take the derivative of the numerator, lo and behold, you've got a product to deal with. So you have to go first times derivative of the second plus second times derivative of the first. And when you go to take the derivative of the second, you run into the fact that this is a square root, so you got to go x squared plus 1 to the 1/2. So it's going to be 1/2 times this to the minus 1/2, and then you get the chain rule on top of that, and then you probably lost your place unless you're doing it one step at a time. And by the time you're done with it, you filled up the whole page with the computations, and chances are you might have made an arithmetic mistake or a minus lost somewhere, and then you get frustrated. So people have been looking for simpler ways of doing problems like these, and there is a simpler way if you're willing to take an extra step to begin with and deal with logarithms. The nice thing about logarithms, one of the nice things, is that logarithms play very, very well with exponents and products, this is a multiplication, and quotients. Radicals are exponents too. So anytime you've got products, quotients, exponents, especially all lumped together like this, logarithms are going to be wonderful for you. So what you do in this problem is you say, what if you start by doing something other than taking the derivative? What if you take the log of both sides? That's legal. You're allowed to take the log of anything. Well, take the log of both sides to preserve a true statement. Now we're not finding y prime yet. We're doing a little algebra. The log of y is equal to the log of this mess. So I'm taking log of both sides, right? Now, what is the log of that big mess? I'm not going to write it that way. I'm going to use one of the laws of logarithms. Well, what is this mess? What kind of thing am I dealing with from the executive point of view? Well, I said it already. It's a quotient. And the log of a quotient, remember, log of a over b is the log of a minus the log of b. So I'm going to get the natural log of the top, x to the 3/4 times the square root of x squared plus 1, that's the log of the top, minus the log of the bottom, 3x plus 2 to the 5th. Okay, the log of both sides. Now I'm just still going to do algebra. I'm going to wind this down as far as I can go. So natural log of y equals, now log plays well with products, so it's the log of the first, log of x to the 3/4, plus the log of the second, natural log, of square root of x squared plus 1. Minus, now here I've got log of 3x plus 2 to the 5th, and log plays well with exponents. So this 5 is going to come down here times the log of 3x plus 2. So far, just algebra. Okay, and I'm still not done because I can do more algebra here that's not too hard. Log of x to the 3/4 is just 3/4 log of x. I just used that rule a second ago over here. I use it over here. And while I'm at it, this one too. X squared plus 1 to the 1/2 is the square root. So this is going to be 1/2 log of x squared plus 1. Now, here's a thing that you have to be very careful about. Log does not play well with sums and differences. So log of 3x plus 2 you're just stuck with. Log of 3x plus 2. Okay, so we've done as much as we can with this, but we've rewritten this log in terms of things that are not too nasty. Now I can take the derivative of both sides, with respect to x. So the derivative of the left with respect to x is the same as the derivative of the right with respect to x. And really the hardest part for people seems to be the simplest, which is right here. What is the derivative of the log of y? Well, you have to remember what y is. What is y? Well, remember what y was way up here? Y is this horrible, big, complicated mess in terms of x. So this is not just simply log of x. This is the log of a complicated function of x. So what's the derivative of it? Well, the derivative log of anything is 1 over that anything. But the chain rule, of course, comes in and says you got to multiply by the derivative of what's inside. The derivative of y, which I'm just going to write as dy dx, or y prime if you prefer. Okay, now take the derivative of the right. And you'll notice the derivative of the right is not too bad. The derivative of 3/4 times log, the 3/4 is a multiplier. It sits there and watches while you take the derivative of log, and we know that that's 1 over x now. Plus, what's the derivative of 1/2 times something? Well, that's 1/2 multiplier, sits there. What's the derivative of log of anything? That's going to be 1 over that thing, squared plus 1. But wait a minute, this thing in here is not x. So the chain rule says, wait, you got to multiply by the derivative of what's inside. So I'm going to get a factor of 2x. And that's it for that part. Minus, once again, 5 is a multiplier, so it sits there, times the derivative of log of anything gives me 1 over that anything. And then the chain rule comes along and says, oh, you got to multiply by the derivative of what's inside. Big deal. That gives me a 3. Okay, well, I'm about done, believe it or not, because here's dy dx, so I can solve for it. dy dx equals, now I multiply both sides by y, so I'm going to have y here, but now I'll remember what y was and go ahead and write it out in all its gory detail. It's x to the 3/4 times the square root of x squared plus 1 over 3x plus 2 to the 5th times that mess, whatever that is. So we just simplify that. That's 3 over 4x, that first term, plus this guy, the 2's cancel, and I'm left with x over x squared plus 1. And then minus, this is 15 over 3x plus 2. Final answer. There's not much that you can do with this. This is it. This is the simplest that we're going to get it. Notice, I never had to use a quotient rule or a product rule. And the amount of chain rule usage was really fairly low level. This isn't too difficult. You're not pulling your hair out with all the computations that you'd have to do with this. You might compare it. If you think that this is too nasty to figure out, try taking the derivative of this your way with the quotient rule and the product rule, and then see which one you prefer. Let's review what happened here, because this is worth reviewing. We have this mess that involves quotients and products and exponential functions, and we think maybe logs will help. So what do? We take the log of both sides, and we don't do any derivatives yet. We're dealing with the log of both sides, so we're just simplifying it down using laws of logarithms. When we get down to here, we're done using algebra, and we take the derivative of both sides. The tricky part may be on the left, because the derivative log of y is 1 over y dy dx. 1 over y times the derivative of what's inside y. And on the right, we just take our derivatives carefully. But then we're about done. This doesn't take long. And then we just push y to the other side, and we're done. Multiply both sides by y. Okay? It's a very straightforward sort of thing. Now, as I said, this is an instance where you really didn't need logarithmic differentiation. But let me give you an example where you really do, unless you come up with an equal sort of trick, one that is not a trick that you would think of every day. But we're going to do it with logarithmic differentiation. Let's find the derivative of sine of x to the log of x power. Now, before I do this, let's not do all of the horrible mistakes that people can make. This is not the power rule, the high school rule as I call it, because log of x is not a constant. You can't go natural log of x times sine of x to the natural log of x minus 1. If you do that on a test, you will lose full credit for the problem, plus I'm tempted to take off points on other problems. So don't do that. The log of x is not a constant. You can't use the power rule when this is not a constant. Okay, so you know it's not a constant, so it's an exponential function. But if you've memorized the formula for b to the x, you write b to the x times natural log of b. That's not right either, because this is not a constant either. So what I'm trying to say is we do not know how to do this yet. We haven't done this before. So we're going to use logarithmic differentiation. And we start by saying let y equal that thing that we don't know how to do. Everything is easier when you've given it a name. You then begin to have power over it. Okay, so we've let y equal this, and what are we going to do? We're going to use logarithmic differentiation, the idea that logs play well with exponents. This is an exponential expression. So what if we take the natural log of both sides? That would mean the natural log of y is equal to the natural log of the sine of x to the natural log of x power. Now don't get lost here. Don't get confused. This is the log of this big horrible mess. And this big horrible mess is an exponential expression. So that exponent can come out as a multiplier. So here's what you get. Natural log of y. Let's go ahead and write parentheses for everything here. Sine of x, natural log of x. Okay? So we know what functions are. Natural log of y is going to be equal to, here's this natural log of x coming out as a multiplier. So we get the natural log of x times what's left? Natural log of sine of x. Okay, that's because logs play well with exponents. They knock exponents down. Okay, next, we're done as much algebra as we can do. We now take the derivative of both sides with respect to x. All right? On the left, the derivative of log of anything is going to give us 1 over that anything. But that anything is not x. We're taking derivatives with respect to x. This is not x. This is some horrible complicated function of x. So we got to multiply by dy dx, the derivative of what's inside. On the other side, we've got a nasty product rule to contend with. Not much that I can do about that. I'm not going to use logarithmic differentiation on top of that. Don't go there. So we'll take the derivative of this product using the product rule. So the product rule says the first times the derivative, I'll write it out, the derivative of the second, the derivative of the log of the sine of x, plus the second, the log of the sine of x, times the derivative of the first. Well, I think I can handle that. The derivative of the log of x is just 1 over x. Okay, next line, 1 over y dy dx equals natural log of x times what? What is the derivative of the log of the sine of x? Well, the derivative of the log of anything, we know, is 1 over whatever is there, 1 over sine of x. So we write that, 1 over sine x. But sine x is not x, it's a function. So the chain rule says, you got to multiply by the derivative of what's inside. Fine. Derivative of sine is cosine. Here we don't have anything more to do. We just write log of sine of x times 1 over x. And now we have our answer. Because here's dy dx. We multiply both sides by y, which was what? It's up there. Y is sine of x to the log of x power. So we just write sine of x to the log of x power times all this stuff. I mean, you're multiplying both sides by y to get rid of this 1 over y here so that we have dy dx all by itself. So you multiply both sides by y. Here's y, and here's the rest of that junk. I'm just going to put it in the parentheses here. Okay, but before I do, notice what the answer is. Dy dx for a function like this is that function back again times blah, 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 blah. Well, that shouldn't be a surprise to you. The derivative of any exponential function is that exponential function back again times some horrible mess. In this case, it's certainly not the log of the base, like it was in the case of b to the x. In this case, it's this thing, which is, well, you could write it in a clever form here. You could write natural log of x times cosine over sine is cotangent x, plus log of sine of x divided by x. And we'll leave it there. That's plenty good. You didn't even have to do this if you didn't want to. Log of x times cosine of x over sine x is perfectly fine. Now, wanted to point out another thing. That is that a lot of people have trouble with the difference between the log of x times something, which is what you've got here, log of x times something, and the log of something. This shouldn't be a problem by now, but people may not have had the pre-calculus background that they should have. Log is a function, so you have to know what is being plugged into it. In this case, we're taking the log of both sides, so what's being plugged in on the right is a horrible mess. But it's the log of that thing. And that thing does happen to be an exponential, so the exponent, using the law of logarithms, can come out as a multiplier. So some people might just write log of the log of that thing. And you see that that's wrong. This log of x comes out as a multiplier. It comes out of the log as a multiplier. So it's log of x that is multiplied by the log of the sine of x. It's not the log of the sine of x. Okay? So just make sure that you understand the difference between log of x coming out as a multiplier and log of that whole quantity. All right, and I think we've all suffered enough. That'll be it for now.